My pronouns are she, her, and I'm the Access Officer for Oxford University Physics Department. What that means is that I run most of our secondary school programmes for students like you, including all of the stuff to support people interested in applying to study physics here in Oxford. This session is being recorded and will be made available to you tomorrow. Let's start though with a quick reminder of the housekeeping rules for those of you on Zoom. You are able to use the Q&A today for any questions that you would like to be addressed, and I'll let you know when this is switched on. You should already be able to access there, but I won't be taking questions straight away while I'm doing this. You can also access the chat to share any thoughts, but please make sure you keep it polite and kind. Don't share any personal details or information, and also don't use it for questions that you want us to answer. Pop those in the Q&A. If at any point tonight you're feeling unsafe or concerned about anyone, you can also contact safeguarding@physics.ox.ac.uk and we will get back to you as soon as we can. Let's get started though. Before we jump in with our students who are taking you through some problems today, I'm going to give you a very quick introduction to the course and to the PAT itself. Lots of you are joining us for the second, third, fourth, fifth, even sixth time and already know this bit. If that's you, just take a minute, get yourself a cup of tea or your drink of your choice. If you are new, hopefully this will answer some of your questions. So the PAT is the Physics Admissions Test. It is the required test for physics, physics and philosophy, engineering and materials science. This means it is a test that must be sat, and the result on your PAT forms part of the information which we use to decide who we're going to shortlist for interview. In order to sit the PAT, you must register as a candidate. Your school do not do this for you. The PAT this year is on screen and entirely multiple choice as it was in 2024. It's also a really similar format to tests like the ESAT, the BMAT and the LNAT, so it's quite a well-established formula. We've worked really hard behind the scenes to make sure we can gain as much information as possible from this format, so the answers are not just 1 or 0 marks. The syllabus is unchanged and the questions are really similar in style to previous years, which is why we've not changed this course itself. You might also want to bear in mind that the online test includes a built-in on-screen calculator, which looks exactly like a regular calculator, works in just the same way. There's a practice of the test format available online, which I share in every email. Again, something to keep in mind is that practice is just to get you used to the digital format. It's not a true reflection of the balance of questions that you might expect. That's the PAT then. What is the PAT prep course? So this is a course that we run in the physics department on behalf of all other departments and subjects who require the PAT. The course is a set of 8 webinars, along with problem sets and a summer assignments and a few Isaac boards as well. And we hope that this course provides you with all of the information that you need to take the PAT, to help you prepare for the PAT and to be confident going into interviews if you're shortlisted. The timetable on screen at the moment is part of the timetable which is at the bottom of every PAT email, and I always highlight in yellow where we are. You can see this is from Study Focus 3, so this is how it looked last week. This week the next section is highlighted and it's letting you know that we are going through solutions to problem set 3. All of the information about our course and all of the course materials are on the course materials page. And I link to this at least once, usually twice or 3 times in every email. At the moment, that page looks like this. And you can see we are down here at the bottom where we are in the 17th of September. Solutions Webinar 3, it tells you what the topic is and gives you a link directly to our YouTube page. Above it, you can see the problems that were shared with you and that we asked you to solve in advance of webinar 6. At the top of that page, there's also an introduction to physics problem solving, which our colleague Rachel developed in the first webinar. And I've put a link to a Pearson VUE website, which is a video guide to the test centres themselves. Moving on, this is a quick reminder that all of the information about the PAT that both you and your school need can be found on this page. So ox.act.uk and then admissions tests. This link is in all of my emails once again. It's the most up-to-date page and this is the one to check first for any information that you need. It's also got an FAQ page which is really useful. Some key facts to finish up. A reminder that all tests this year are sat at a Pearson Test Centre. There are venues in almost every country around the world. And when you register, you'll be able to select a centre which is most convenient to you. For some people, it might involve travel, but hopefully not too much. And again, same arrangements, LNAT, BMAT, and the Cambridge Admissions Test. The PAT is completely free to register for, and if you're eligible for any access arrangements such as extra time, you can apply for them when you register. Registration is only open until 2 days' time, the 19th of September. So make sure you are registered for the PAT this week. Register today after the PAT session, register tomorrow. Give yourself time that if something goes wrong, you've got time to contact us and fix it. You'll be contacting our test team directly. There is nothing that I can do to help you. Once you're registered, you can also book your test, and that is open until the 26th of September. So you've got 1 more week. And then the PAT will be on the 22nd and the 23rd of October. As I already mentioned, that test format is different. We don't want you to be scared. Here is where you can link to the sample PAT, and it also lets you access that calculator. You can go into that as many times as you like. That is my quick PAT introduction. I hope it was helpful. Those of you who have seen this 6 times, you can come back now. We are ready for you. I'm going to stop screen sharing. And I am ready to hand over to our 2 lovely students who are joining us in their summer break to present their solutions to the problems which we shared with you last week. Let me go and get a copy of those problems. I will take you through and we'll see where that gets us. So I believe, Ryan, you are presenting your solutions first. So welcome. And I know Ryan was having some internet difficulties earlier, so hopefully he will be able to get back online and introduce himself to us.
All right.
There we are. Hey, Ryan.
Hi. Yep. Can you hear me?
Yeah, we can hear you perfectly. I was wondering, just before you get stuck in with your problems, could you tell us a little bit about where you are in your Oxford physics journey, please?
Yeah, sure. So, my name is Ryan. I am going to be a third-year physicist in the coming school year, and I'm a member of Jesus College.
Lovely. So for anyone who is interested in colleges and things, that's maybe something we can talk about later. But for now, Ryan, over to you. I am going to switch my camera and microphone off. I will be sitting in the background answering any questions that come through on the Q&A.
And just wondering, do I have permission to share the screen?
Absolutely, you should do. Yep. Perfect, we
Okay.
can see that nicely.
Okay.
Thanks so much.
Yeah. Can everyone still see the screen? Okay. Yeah. So I'm going to start off with by sort of answering questions 1 to 4, and then Wei is going to take over for questions 5 through 8. So the first question, we are talking about a marble in a fishbowl. And what we want to know is how big of a kick can we give the marble so that the marble still ends up in the fishbowl. And with these type of questions where there's a lot of sort of geometry in the problem, the first thing you would want to do is sort of obtain to the best of your abilities an accurate sketch of the problem, like so. And so here we have sketched a fishbowl, which is 2/3 of a circle, fixed as described in the problem. And then we have a marble at the bottom, which we're going to kick. We'll give it a velocity v naught here. And as the marble moves up the fishbowl, there are some different scenarios. And we're going to think about that. So first, we can say maybe the marble isn't fast enough and it will probably fall off before it even reaches the edge. Then it will certainly end up back in the bowl. So we don't have to worry about that case. What we're interested in is when v naught is really big. So the marble will fly off this edge. And it'll fly off this edge at a tangential to the circle with velocity v1. And so look at what values V1 can take. And so, for example, certainly V1 can be as small as possible. In that case, the ball will just fall back into the bowl. But if we make V1 a bit too large, it will go on a parabola trajectory and fly out of the bowl. So what we can do is we consider the limiting case when V1 is just small enough such that it reaches back on the other edge of the fishbowl. And the way we can do this is we can calculate time the marble spends in the air. And we notice that in this diagram, when the marble leaves and when it comes back on the other edge, the y velocities reverse. So we can calculate the time of flight very simply by using the initial y velocity, subtracting off the final one, and we get 2v1 times sine theta over divided by the gravitational acceleration, and theta where we've described as this angle over here. And so we then require basically that the x component velocity, so the x distance traveled in horizontal direction, is smaller than the width, this width here of the bowl, because otherwise it will fling out of the bowl. Okay. And we can do a bit of simple geometry, and we have that the horizontal distance will be 2r times sine theta. And it will be simple geometry as well to get the x velocity as v1 times cosine theta, and the y velocity as v1 times sine theta. So if we put all these symbols into our equation, we obtain the following. So v1 squared is smaller than rg over cosine theta. And the problem now remains to determine what is cosine theta. And we can look at this helper diagram here, where we have isolated a triangle containing theta. And if we look at the side length, we can easily see that cosine theta is simply r over 3 divided by r. So cosine theta is just 1 over 3. So here we have v1 squared is smaller than r times g over 1 over 3, which is 3rg. So it seems that we have solved the problem. But the actual question wants us to tell us about v naught. And this is done by doing energy conservation, because since we're also assuming that the fishbowl sort of is smooth and the marble doesn't experience any air resistance or friction from the surfaces. So what we have is the initial kinetic energy, so 1 over 2 times mv1 squared. Oh, sorry, I'm sorry. The initial kinetic energy is on the right here, because we're initially only giving in the kinetic energy. And on the left, we have the final kinetic energy plus the gravitational energy gain. And here we take the limiting case that v1 squared is equal to 3rg. So all of these quantities are known except v naught squared, and we can compute v naught squared. And we have that v naught is square root of 17 over 3 times r times g. Does anyone have any problems with this?
Ryan, I was just going to jump in. That felt like a perfect pause. We've had somebody ask in the Q&A why both of your angles are the same, that one and the velocity one. So you might need to go back a tiny bit for that.
Yes.
Thanks so much.
So we can. So here, because when the ball flings off the fishbowl, we're doing it at a tangential sort of direction. So this angle here, the angle between v1 and r is actually 90 degrees. Now we've drawn this angle to be 90 degrees as well. And if we do some simple geometry, we have that, I'll use a pointer. This angle here, let's call it x. Sorry. This angle here, x, plus theta will be equal to 90 degrees. And this angle plus this theta would also be equal to 90 degrees. So these two angles are equal.
Thank you so much. And we had another one in the chat where someone's asked, how does 2r sine theta come from? And I'll be nice, I'll answer it even though it was in the chat, but do put them in the Q&A for us, otherwise they get a little bit lost.
So do I answer it now, or?
If you're able to, that would be absolutely great.
Yeah,
It gives
I
everyone
can.
a sec before we move on. Love your slides as well, they're great.
What we want is to calculate Sx, which is this distance here. It might be difficult at first, so we consider half of it, which is here. Now, if this is r, this distance, the red line highlighted here. I'm sorry, there are red spikes appearing everywhere, just my laptop. That divided by r is sine theta. So this line here, draw a different line. This orange I have highlighted is simply r times sine theta. And Sx is double that. So Sx is equal to 2r sine theta. Is it all right if I move on then?
Yeah, I think we're good. Give us a thumbs up if you're ready for us to move on. Perfect. Thanks so much, Ryan.
Okay. And the next one we're looking at a sort of a equilibrium problem. So nothing is moving now. And we're given some real numbers as well. So for these type of problems, where we have something in equilibrium, it's usually the best way to start is by labeling all of the forces acting on a body of interest. And here, our body of interest is the two trusses, and we want to know if they will fall, or sort of, sorry, if what's the resulting tension in the rope. And so the first step is to draw a very detailed diagram again. Diagrams help a lot in these questions, and especially a lot of the problems don't actually give you the diagrams to begin with, so it's very helpful for you to draw one like this. So here, the triangular sides are the two, sorry, wait. The triangular sides are the two trusses, and we have the rope here, like so. We've also labeled some of the distances. So we know that the weight of one of the trusses is acting on the wooden truss in the middle, like so. So it's 1.5 meters away from the top, basically. And we also know that it's given that the rope is tied 1/6 of the weight of the trusses. So 3 divided by 6 is 0.5. So this distance here is 0.5. Some of the other forces worth mentioning, of course, is we have the sort of normal contact force from the ground that's pointing up. And because we have said that it's on an ice rink, which means that we could totally ignore friction, there will be no horizontal contact force. So the contact force or the normal force, the reaction force, will be pointing straight up. And from this, we can immediately calculate something. So first of all, in equilibrium, the net force must be zero. So we start by calculating the vertical force balance. So vertically, this truss experienced some forces. So we have this, the force from this weight of the ball pulling it down. That's what I've called F ball. We also have its own weight pulling it down. So 1W here and 1W here. So that's 2 Ws. And all of this is countered by the reaction forces, coming from the contact edges here. So it will be R plus R, which is 2R. And so this gives us one equation, which doesn't really solve a lot of things. Because from this, we can get what R is, but we don't really know what T is. To connect T, we can look at another condition of equilibrium, which is that the net torque on the system should be zero. And in particular, the torque on the right truss would also have to be zero, since the net torque on the system is zero, the right truss will also have to be in equilibrium. And we can do this by sort of resolving the components of the forces perpendicular to like the pivot point, which we've taken to be this top point here. And keep in mind that torques are calculated based on the perpendicular distances. So if we take the component of the forces that's perpendicular to this line here, we'll be calculating the torque directly. And so we can calculate the counterclockwise moment. So this forces that torques that will be causing this truss to turn this way. And we discovered there's only actually one component, which is this component here, r cosine theta. And it's at a distance 3 meters away. So it would be 3r cosine theta, pointing this way. The clockwise moment in the other way would be w cosine theta and t sine theta over here, if we resolve the angles carefully. And this component here, w cosine theta, will be 1/2 of the way in the truss, so it'll be 1.5 times w times cosine theta. The other component, which is caused by the tension from the rope, would be 2.5 meters away from the pivot point, which means we'll have 2.5 times t times sine theta. And these would have to balance. So what I did here was I equated the two of them, and then I divided by sine theta. Oh, sorry, I divided by cosine theta, and you obtain this equation here. So now we have two equations. One of them is here, and another one is here. We know that what F ball is. It's given to us as 500 newtons. We know what the weight is because they told us what the weight is. So each truss is 40 kilograms, and that gives us about 400 newtons each. And we know what theta would be because we know all of the trusses from this diagram here. We can calculate what theta or the cosines and sines of theta would be. And so first we can calculate what R is supposed to be. So from the vertical balance equation, we can get that R is equal to a half times 2W plus F ball, which gives us 650 newtons. And then using the torque equation, we have that 2.5 times the tension times 10 theta is equal to 3 times R, which is 650 newtons, minus 1.5 times the weight, which is 400 newtons. And if we plug in the numbers for 10 theta and do a bit of math, we can easily arrive that the tension will be 405 newtons. Yep. And questions?
Hey, I'll come back in. So we've got a few questions asking about how you assumed that it was uniform. So I guess this is quite a nice point where we kind of get to make our own assumptions once we get to this point in physics, right?
Yeah. Usually you assume it's unless it's specified otherwise. To make life easier for you, you can assume everything is ideal and uniform, unless it's otherwise specified. It might do you good if you write down these assumptions from the start. So assuming no friction, everything is uniform, no weird things going on, nothing too heavy or relativistic or anything like that. But basically, the sort of logic is that if the problem doesn't say, like, just assume the most ideal case.
Perfect, thank you. And then we had a few people who have said that they tried to do it in a different method. I mean, I don't know about you, Ryan. I always feel like that's absolutely fine as long as your method works in
Yeah,
terms of physics.
yeah. If you can follow the method logically, like if you present it, every step is physically justified, and you can get to the right answer. Like I think it's perfectly fine. Yes.
Awesome. And then got a few questions for me. Where can we find other problems like this? Why didn't you need to consider the perpendicular force of the ball on the right truss?
That's a good point. So, um, here I've taken the pivot. It's important when you're doing torque analysis or moment analysis that you look at you pick where to choose the pivot. And here I've taken the pivot to be at this point at the very top. So there would be forces there, but if we remember, moment is distance times force. The distance of that force is zero. So we can ignore all forces acting on the pivot. So this makes it convenient for me to ignore forces from like the ball because that would like add in some extra calculation that I didn't really want. So I just placed the pivot here to just ignore
Perfect.
so I can safely ignore the horizontal forces from the ball.
Thank you. And I think that covers somebody else asked why you're using torque and somebody asked why that moment is equal to zero. And I think you've just covered both of those in that explanation. What else do we have? We had somebody else. Again, the normal forces question you've just answered. Somebody said they've got 405, but the solution said 400. I think we're fine. Often it's a case of rounding and significant figures. And just one person who's asked about theta. So we might just need to go back to that and then we will move on to make sure we get through all the questions.
Sorry about theta.
Yes, a couple of people have just asked to quickly
Yeah,
recap how you find
sure.
theta. Thank you.
So
Sorry, I know you've not got
there's
great
another
internet.
quantity that I didn't. Sorry. Yeah. Can you hear me?
Yep, all good.
Yeah. So there's another quantity that we forgot to label, which is the length of the rope here. and this is 3 meters. And if we draw here, I'll make a perpendicular line down here like this. We can easily see each half will be like 1.5 meters, which is how we arrived at this diagram here. So this length will be the length of like sort of the truss top to the rope. And this is half of the rope length, which is 1.5 meters. And from Pythagoras theorem, 2.5 square minus 1.5 square, you can verify it's 4, which means this will be 2 here. And then from that, you can do off the tan theta and cosine thetas and sine thetas.
Perfect. Thank you so much. Anyone who's still a little bit unsure, remember you're going to be able to watch back Ryan's explanation as many times as you need. I think we're good to move on. Thanks so much.
Right here. Okay, so this question is quite short in words, which means that usually it's going to be a bit difficult. So first one, we want to show that the maximum range of a cannon on flat ground is achieved by launching at an angle above the horizontal of theta equals 45 degrees. And this is another sort of a dynamic problem, or kinematic, I think. Basically for any problems relating equations of motion, we write down the appropriate Subat equations. And here we can start off by sort of listing off what we know. So first we know that the x velocity is v naught cosine theta. That's easy. We also know that the y velocity is v naught sine theta, which is the initial y velocity minus the gravitational acceleration times the time, which is what I have here. When we launch something on flat ground, it's going to follow a parabola. And if we know about parabolas, it's going to be symmetric about the center. And at the top of the flight, the y velocity will be 0. So we can simplify a lot of calculation by simply calculating the time that the y velocity takes to reach 0 and multiply it by 2 to get time of flight. And we can equate basically this quantity, Vy, Vy equals to v naught sine theta minus gt equal to 0 and multiply by 2. So we get the time of flight is 2v naught sine theta divided by g. So the range of flight is just the x velocity times the time of flight. So we all know all of these quantities. So we have 2v naught squared times sine theta times cosine theta over g. Now, usually when you have like a combination of trig functions, you will sort of want to combine them into simpler forms. And here we notice that 2 times sine theta times cosine theta is sine 2 theta. So this can be written in a simple form like this. Obviously, sine x reaches its maximum when x is 90 degrees. And 2 theta, when 2 theta is equal to 90 degrees, where that theta is equal to 45 degrees. So this basically shows the first part of the problem, that the maximum distance is reached when theta is 45 degrees. Now we have a different scenario where we're launching on a hill. And here things gets a bit messier because we can't really take advantage of the fact that the parabola is symmetric because the hill itself is not symmetric. So here it might do us good to calculate the sort of the motion of the coordinates of the trajectory explicitly. So this is also writing down a few Subat equations. So we have first that the x position is equal to x velocity times time. And this is equal to v naught times cosine theta times t. This is no accelerations in the x direction. In the y direction, we have that vyt minus 1/2 gt squared, so basic Subat equations. And we plug in the values, we get this. Now, normally on a flat ground, we will ask, when does y become 0? Because that's when the ball reaches the ground. But here things are different. When y reaches 0, the ball is actually not on the ground. The ball is on the ground when it reaches the slope. And here you can write down the equation of the slope, which is y trajectory. When sort of the trajectory of the ball reaches negative x times tangent of phi. And we can sort of see this by drawing a sort of a coordinate axis here. So if we have something like this here, that's the y-axis. And then this is the x-axis. This angle will be phi. And so if we, the sort of the gradient of a straight line is the tangent of the angle it makes with the x-axis. Sorry. The equation of the slope would be minus x tangent phi. So this is what we have. We want the y, sort of the y component, sorry, of the position equal to minus x tangent phi, which is what we have here. So minus v naught times tangent phi times cosine theta times t, because x is v naught cosine theta t. This is a quadratic in t, but if you notice, we can divide by t on both sides, which becomes linear in t, which is quite easy to solve. We get this equation here. And like before, then the range will be the x velocity times time. Here, the question I think is a bit ambiguous on what the range actually is. Would it be sort of this horizontal distance here, or would it be sort of be this downward sloping? But in either case, it'll be multiplication by a simple constant. So here I've taken the maximum range to be the horizontal distance. And that will be simple. So it'll just be the x velocity times the time. And we'll get this quantity here. And like before, we convert these to using the double angle formula, and we will reach this formula. And by this point, is there any questions?
Okay, so we've got one. I just didn't quite get to it. We've had somebody ask, why is the time of flight 2 times the time of Vy?
Okay.
And a few other questions earlier.
Yep. I will start here. So normally when we have a parabola, it goes like this. So I'm looking at this point here, which is the top of this motion, and we can agree that it's symmetric about this point. So the time it takes for me to go up here is the same as the time it takes for me to fall down here. And basically at this point, the parabola is sort of flat, like this. There is no y component. So the time it takes for the y component to reach 0 would be half the time of the entire flight, basically.
Perfect, thank you. I'm just typing an answer to another one about assumptions, same time as before. You get to make whatever assumptions make your questions work.
So no air resistance.
Yep, absolutely. Your call. Somebody else, could you just quickly show the slide for part A again, please?
Let me see if I can find an eraser to rub all these out.
Yeah, it's tricky, isn't it? Remember, if not, don't worry, you can go back and you can look at this and freeze it at whatever point works for you. Perfect, thank you. And a few questions just about the gradient. Where did the x come from in the gradient? Why you've used the gradient? So maybe just a quick 30 seconds on gradient, and then again we'll be able to move on.
Yes. So here I'm looking at essentially sort of the intersection between the intersection between this parabola and this slope here. So I want to like sort of label everything in a sort of coordinate system to make everything easier. So I've picked my coordinate system to be centered around here, and I've written down the equations for the parabola. So to find this intercept, I would write down sort of the equation for this line here. And it will be something like y equals to kx. And to figure out what k is, we're going to write down the gradient, which is negative 10 phi.
Perfect. Thank you so much. I think there's a few people who aren't quite sure, but I think our best bet, we are going to move on because we've got a lot of questions to get through today. Watch back the recording, and I'm also going to share solutions to all of these problems in a week or so, so you'll be able to have a look at them as written solutions as well. So between Ryan's excellent solution, being able to watch that back, and our written ones, you should be all okay. Thanks so much.
Yep. Yeah. The last order problem. So once we have gotten this, and here is a sort of a trick you can use that is that if you couldn't figure out part B, they have still given you the formula. So move on to part C, where it's actually you can just use the formula. So here it wants to determine the relationship between theta and phi that maximizes the range. So it basically wants us to calculate theta as a function of phi. So at whatever slope, we can find a theta that maximizes the range. So first we need to consider what quantity is fixed, and in this case, it should be the slope, since like just logically thinking, you can't vary the slope that much. But you could vary the angle of launch, theta. And so we differentiate r with respect to theta, and doing basically trig differentiation, we arrived at this formula. And we wanted to set it to 0 so we can ignore all the previous pre-constants, pre-factors. And what we end up with is tangent 2 theta by dividing cosine 2 theta equals to cotangent phi. And then there is the trig identity, which basically says tangent of x is equal to cotangent of pi over 2 minus x. And so what this says is that 2 theta and phi, the sum of them is pi over 2, which is 90 degrees. And if we revert that to solve for theta, we have that theta is equal to 45 degrees minus phi over 2. And when you get something like this, you can check if it makes sense. So we know that when phi is 0, the angle should be 45 degrees, which is what we have here. So theta is 45 degrees when phi equals to 0, which confirms our answers in part A. Yeah, and this is the last part. Are there questions for this part?
No, I think you're good. Thank you so much. I think just recapping that is really helpful for people.
Yeah. The last one. This one is more of sort of there's a thinking problem essentially. So basically this is a monkey. We want to tranquilize a monkey or shoot a monkey. So the first case, if the monkey does not move, should the zookeeper aim above, at, or below the monkey? And here, like, we just think, like the dart is going to fall from like it because gravity is going to act on it. The dart is going to fall from our initial aim. So like it's pretty reasonable that we should aim above the monkey. Part B is a bit trickier. The answer actually would be that the dart we should aim directly at the monkey. Because we can say that both the dart and the monkey fall at the same rate, which is determined by gravity, and both feels the same gravitational acceleration. If, for example, there were no gravity, we would aim the dart directly at the monkey, like in free space. But with gravity acting on both the dart and the monkey, they receive the sort of same acceleration. They will fall at the same rate. So by aiming the dart at the monkey, you would still sort of hit the monkey, even if the trajectories are curved. This is a bit of a wonky explanation, so you can sort of confirm this by doing the next part of the problem, which is sort of solving this with Subat equations. As usual, we draw the setup like so. So this will be the monkey. This will be the dart, and will be launched at a velocity u across a distance sx, determined by a height h. So in part A, we want to hit the point sx h. And we can calculate a few things. So first of all, we know that the time of flight, if it were to hit the monkey, would be the x horizontal distance divided by the horizontal velocity. And we know what the y positions will be. So if we plug in the time, we have this equation here. Now we can convert a few simple quantities. Vy over Vx is essentially actually V naught times cosine theta. So we have factored out the V naught here. And what we have is this equation here. Now, the curious quantity is sx times tangent theta. And what is this? If we go back to the diagram, um, sx times tangent theta, which is this angle here, it will actually be, if we extend this line all the way up here, so it would be the height we are aiming at. So what we're saying is that the height sy, I'm going to call it, the height we're aiming at is higher than h, the height of the monkey. So this just basically proves that we're aiming higher than the monkey in part. In part B, more complicated, but it's actually quite easier to solve. So the time of flight is still, Sx over Vx, which is equal to Sx over V naught times secant of theta. But this time we need to note that h, which is the height of the monkey, is also a function of time. So the left-hand side of the equation is the same as before, but the right-hand side we need to include a sort of a gravitational free fall, which would be h naught minus a half gt squared. And what we get in the end, these two things, so this and this, happen to cancel, which sort of basically justifies my previous assumption that the rate of rate of their fall is the same because they're both being curved by gravity. And what we end up with is Sy equals to h naught, which means that we're aiming directly at the original position of the monkey. So in part B, we aim at the monkey. Questions?
There's only one so far. For part A, the answer depends on how far you are from the monkey. So how can you objectively say you should aim above the monkey? So I guess, does it matter how far you are from the monkey, Ryan?
Well, it depends on like what you want to know. So if you want to know like exactly where you want to aim, then yes, it does. But here we'll ask your name, is it above or below? And if we look at this equation here, secant square theta is positive as always. G is just a constant, it's positive. This square here is also positive. So we're having Sy minus the positive quantity that is equal to H. So what this says is that Sy is greater than H, which would be we're aiming higher than the monkey. It's just a matter of how much, basically, if you're further away or further closer. But you're always aiming above the monkey.
Perfect, thank you. In that case, I think you are good to move on.
Yep, I think that's the last of my set of problems.
In that case, Ryan, I believe you are going to disappear after this, aren't you?
Yeah,
Okay.
actually, yeah.
In that case, Ryan, thank you so much. I hope you've all enjoyed meeting one of our almost third year students. There you are. I just thought I'd let you get all of the applause and the hearts before you disappear. So one of the things I get to do in my
All right,
role
I
is
should
work
stop
with our
sharing.
lovely ambassadors. So I like to make sure they feel appreciated. Ryan, enjoy the rest of your break. I will see you when you're back in Oxford in early October. And for now, please let me introduce one of our other students, Wei.
Hi, I'm Wei. I just finished my fourth year actually, so I'm a recent graduate. But I'm coming back to Oxford for DPhil. My undergrad is at Hartford and my DPhil is at Balliol. I want to apologies in advance because just now I have some issues with my internet Wi-Fi. I don't know what's going on, but hopefully that thing doesn't appear anymore. Um, so
Well,
yeah.
you're coming through nice and clear now. I'm online to jump on if we have any issues as well.
Okay. So I didn't prepare any like PowerPoints or slides.
Yeah,
I
Ryan's very
was
slick, isn't
going
he?
to, yeah, I was just going to use my iPad and let me see if it worked.
I like it because actually this gives us two completely different approaches to problem solving. And I think for me, I'm just going to ramble while you sort yourself out, why?
Yeah.
For me, this is really important. Like we get a lot of questions about, can I do it this way? Can I do it this way? What assumptions can I make? And the answer is usually, as long as it's physically true, you can do whatever you like. And that's a big transition to university physics, which is as long as the physics makes sense, you can make your own choices. So I can see that you've started screen sharing, but I can't yet see your
Yes, it's still
screen.
loading somehow. Hopefully. Okay. Did you see
Ah,
it?
there we are. Yeah, perfect.
Okay. So but could you see it?
I can see, yeah, I can see your mouse moving. You're getting thumbs up. I think
Okay.
everyone else is good.
Okay. Okay. Let's try again without my video open.
Yep, that's perfect. All
Is
good.
it better this time?
Yep.
Okay. Okay, let's try this way, although might be a bit difficult, but yeah. So just let me know if any questions
I'll keep
without
an eye on the chat for you and kind of interrupt if there's good moments.
Okay, cool. So so question 5 is basically a motions graphing question. So we'll ask to show and sketch the motion time graphs, displacement time, velocity time, and acceleration time for each of these 3 cases. So the first one is basically just a simple projectile. So imagine throwing a ball upwards, and then it's a projectile without any horizontal placement. So just throw us up vertically and then falls down back, basically. So we could start by I always find these kind of questions easier to start when thinking about acceleration first, because that's always the simplest case. So for example, here for a projectile, we know that the acceleration is always, so if I say this is time and this is acceleration, then it should just be constant because there's no external force applying on it apart from gravity. So it'll just be a constant line here at minus g or minus 9.81. Yeah, so this is when we define upwards as positive. You can like by all means define downwards as positive, then this will be a positive line here. But yeah, I think it's really important to define your directions and stick with them. So after identifying the acceleration time graph, then we could just integrate to get the velocity time graph by finding an initial condition. So here, initial velocity is 0. Sorry, initial velocity is not 0 because we throw it out with a velocity. So there will just be a constant line here going down. And if we start from v0, it should end up as minus v0 as well. Yeah, and the gradient of this line should be the acceleration. So this shouldn't be very hard. And then we could integrate this again for displacement. So if we integrate a straight line, it should be a quadratic line. And here we just have a nice, oops, sorry, projector like this. All right, it's not very nicely drawn, but yeah, it's a quadratic pattern. And it's also not very nice, finally. Okay, yeah, this looks better. Okay, so that's basically part A, a simple projectile case, and then we move on to part B, or the second case where we are traveling by train. So the 2 parts of the journey from Oxford to Banbury and from Banbury to Birmingham should be symmetrical. So we just look at one case first. If I change another color for this, so here so this part, and now we'll look at this part. So again, I like to look at acceleration first because that's simpler. And here we're told that it only takes a few minutes of constant acceleration, deceleration to get to the top speed or come to a stop. Otherwise, it's constant velocity. So the acceleration should only be on 0 at when we are accelerating or decelerating at the start and end of the journey. So that would just be some short time here when we're accelerating, and after some time decelerating when we stop at Banbury, and then we start again from Banbury and go to Birmingham. So the distance or the time taken here, I guess it's like Banbury is closer to Oxford, so it might take a longer time here than here, but this is really arbitrary. Oops, I should close this. This is really arbitrary. So this is acceleration graph. And then we could just find the velocity graph. Again, by integrating or just by like intuitively looking at this. So when you integrate a rectangle like this kind of step shaped thing, it will give you a trapezoid. So like this rapid increase should give you a sort of a linear line, like you're accelerating over this time graph. So that's this part. So this time you should be accelerating. And then for this time, you just constant velocity, and then you decelerate here. And then after a while we're stopping at boundary, it's the same thing again. And we are at Birmingham. So that's the velocity time graph. And then for displacement, so this is a little bit trickier, but it's still the same if you basically a linear graph, if you integrate it, it gives you a quadratic or at least some curvature of a line. And then constant velocity will just give you a linear graph, and then some other ways. So here, if we start from 0, so for this part, it will be increasing more and more. Like the curve of the graph should be increasing because the velocity is increasing, something like this. And then for this part, it will be constant gradient. So maybe I should draw it like this. And then for this part, it'll be constant gradient. And for this part, the gradient will be smaller until 0, because here we had 0 velocity. And then it's the same thing here. So we're just drawing this all the way again. And then same velocity. Oops, it's not connected very well. And then here, yeah. So here is so this is a better drawn graph than my hand drawn graph. But yeah, the idea is the same. Once you get it, it should be pretty straightforward. Okay, so that's part B. Now let's go to the last part, this part. So now we are basically, there are 3 stages of this process. When the football is dropping with air resistance, when it's bouncing elastically, and also when it's after bouncing, which is basically another projectile, same as part A. So we just need to look at the first part and then the second part. The last part should be exactly the same as the first, as part A here. So if we look at, again, acceleration first, so A, T. The first part, when a football is dropped from a great height, that should just be, without air resistance, that should just be free fall. So you have so you should have a constant line here. But now with air resistance, this gravity should be resisted and it should decrease over time, right? So we could have something like it starts as gravity and then it decreases either as a linear line or as a line with some curvature. It doesn't really matter. It depends on how air resistance really works and how you assume it. But here, as long as it decreases, I think it's fine until you reaches terminal velocity. So that is when air resistance balances with gravity and you have 0 acceleration. Okay, so we could stop here and finish the corresponding velocity part. So that would just be you start from 0 velocity because it's dropped from stationary. And then your velocity should be, because you're going down and it defined upwards as positive, so velocity should be negative. So we started by having a gradient of minus g, and then the gradient actually decreases as my acceleration gets less negative. So until I reaches 0 acceleration, and this is when my velocity stays the same, which is my terminal velocity. This is my terminal velocity. Okay, so that's the first part of and displacement. So that should be when we started at some height. We started at a great height, so somewhere here, and then again it should be decreasing, but at a greater and greater gradient, so like faster and faster until it reaches a constant gradient, which is our terminal velocity. So something like, let me try to draw this carefully. So faster and faster, and then here we reach its constant velocity. So like this. Okay, something like that. And then we are bouncing. So at this point, we're bouncing. So we have 0 acceleration. When we bounce inelastically, imagine you have a ball bouncing inelastically. At this point, you must have this acceleration to be positive, such as it bounces back with a positive velocity. So like if this is your ball, and it's bouncing, so it initially has a negative velocity going downwards, it must have some positive acceleration here, such that it returns with a positive velocity after bouncing. So here we just have suddenly a positive direction, a positive acceleration, and then after which the ball leaves the surface and it's no longer in contact with the surface, which gives its normal force for this positive acceleration. It will just quickly returns to the case of free fall, where it's just like simple projectile because it doesn't have a resistance anymore. So that's basically going back to part 1. So this part onwards should be the same as this part. Right. So let me just do the rest for the velocity and displacement time graphs. So with this positive acceleration, our velocity turns positive as well because we're going upwards after the bouncing. So something like this. So a abrupt change of directions. So we go to positive and then it's just linearly decreasing because of a constant minus gravity here. And then for the displacement time, it'll just be a projectile that we have here. So this is the same as this, and this one will be something like this, I think. Okay, yeah. So this is basically question 5. Any questions?
I think you're good, actually. We had 1 or 2 comments about people actually really liking these, which is great. We have had one question, and I'd just like to remind everyone, please keep them in the Q&A because then all the answers are in one place. But that question was, so would a multiple choice question make us choose between graphs? And absolutely, this would be really easy to translate into a multiple choice. I can't guarantee there will be an image choice question, but there certainly could be. It's perfectly valid. But yeah, I think we are good. You've had loads of thumbs up. Let's see question 6.
Okay. Yeah. So yeah,
Totally
question
different.
6 and question 7 are just like messy resistors question. Well, question
Yeah.
7 is less messy, but question 6 is it does take some time. So I'll try to do this as clearly as I could, but feel free to stop me at any point or like
Thanks
if
so
my
much.
handwriting isn't like reasonable. Yeah. So we're given this very messy resistor diagram and we want to simplify it to this thing. So these are here in case we have trouble finding it. But so let's start by identifying something that we can simplify. So basically what we can do here is just trying to find firstly points of same voltage. So we could just simplify the diagrams. For example, here, this is a little bit messy, but actually, because this and this and this should all have the same voltage. So we could actually just ignore this too, and we could just save it with this one. Because, yeah, it could be simplified this way because they're the same voltage. And similarly here, like, it's a little bit weird to look at it this way when you have like crossing lines here, but because these 2 points have the same voltage, we can actually separate it to be something like this instead, which is in a more familiar case for me actually. I don't know if many of you are familiar with the crossing, but yeah, just separating it into 2 parallel circuits works here as well because these 2 points have the same voltage. So that's one bit. Another bit is just trying to identify parallel circuits and series circuits and just simplify all the resistors together until we get down to one resistor in the end. So let's try to do it step by step. So firstly, after this one, we have a few parallel resistors that we can simplify. So the first one could be, for example, here. So here it looks weird, but if you just like this tangle this thing, it's actually just a simple parallel resistor setup where this is 10 ohms and this is another 10 and this is 20 and then yeah, and then it connects from here to here. So that's basically the setup, and we can simplify this if so this is in series, so that adds up to 20 and this is 20 at the bottom And if you do the calculator, or in this case, you just halve it because these two are the same, we get that we have a 10 ohms equivalent resistor here for this setup. So that is this part. And then what else can we simplify this? Okay, so for here, we have one big series line here. So all these, they are connected by one line. So we could just simplify this, and this will be one resistor of 23 plus 40 plus 37, which is 100 ohms. Okay, so that's something that we could do now. Let me just try to use another color because I've used blue here. So this is another, okay, maybe this is better. This is another parallel circuit. And you could just press the calculator. This should give you 8 ohms. So 1 over bracket 1 over 10 plus 1 over 40. And this should give you how much? 12. Yeah. And then after we have this as one circuit, we actually have this with this circuit combined plus this circuit in sorry, I keep saying circuit instead of resistor, but like this resistor in total, which is 10 here, in series with this resistor, which is 15 here. So we should actually combine all these, this plus this, as a single resistor of 25 ohms. Okay, so let's try to redraw the graph here. It's getting a bit messy. So what we have is we have this battery, and then we start here. We have a 4 ohms resistor, and then we go here. We have a 8 ohms, and here is 12 ohms. Then we go here. We have a 25 ohms, which is this one. And then we go this way, we have another 16 ohms one, which is this one. And then we have these 100 ohms thing starts from here and at here, right? This points and this points. But instead of drawing them all the way from here to here, we could draw them in another direction, which is from here to here. But it's the same because start and end point are at the same voltages, these two nodes. So this is the 100 ohms that we have. So that's a simplified version. And we just go from here. So let's try to identify some more parallel resistors set up here. So these two are actually a parallel resistor because, yeah, if you try to stretch it from these 2 points, and you see that they are indeed parallel resistors. So this will just be, yeah, if you stretch it out, it'll look something like this with 25 and at the top and 100 at the bottom. And if you press the calculators, this will give you a 20 ohms resistor effectively. Okay, and then if I simplify this one more time, I will have this battery and then a 20 ohms here, 8 ohms here, 4 ohms here, 12 here, and 16 here. At this point, I believe like most of us should be able to do this. So this bit are 28, so I'm just going to cancel this, erase this, and write this at 28. And then these will be a parallel resistor again. If you do the calculation, this would give you a 3.5 ohms here, and these two are in series. So I'm just going to write it as 28 here. And so these are series. So in the end, we have 31.5 ohms, which is the answer for this R total. I hope this is straightforward, but let me know if there's any questions.
No, I think you're good. We've got no complaints, all love hearts. Again, the only thing that came up was someone saying, could I group it in a different way? And just, there are no, of course. There are no
Yeah, all this.
specific, you must do it this way. It's really different to the way that we mark school exams. We're just happy for you to do it. Last one, someone said, wait, aren't those two in parallel or in series? Probably just depends on the way that you've grouped it, I would guess, for the person who's asked.
Yeah, or like which two are you talking about
Yeah, I'm not sure.
specifically?
I think we're good because I think the method on this one is clear.
Okay.
So if you're not sure any particular, run through it again. But I think you're good, Why? Thank you.
Yeah.
I want to see
And
you do the cube.
yeah, tricky one. Okay. Um, so last question of today, we have this a little bit tricky thing. Um, but once you get the trick, it should be pretty straightforward. So the question is basically asking, we have this weird setup. I mean, who wants to make resistors align in this way? But so we have this setup of how many resistors? 12 resistors in a tube setting, and we're connecting one N from A and another N basically at every single other point. Oops, I didn't erase this carefully. So one N at A, and we want to know if we connect them at B, at C, at D, and any other points, what are the um, effective resistors that we're having? So that's the question. So here, I mean, one way is to just draw out the effective resistor diagram for each of the 12 cases, or not the 12 cases, for the how many cases are whatever cases are here, and then yeah, and then say what voltages and what resistors there are effectively, but that will be a little bit complicated. Another way is to try to find symmetries here, and or like which points can I treat the same way, like which points are symmetric effectively. So one way to think about it is that um, starting from A, there are 3 points. So B, H, and F are the ones that are just one resistor away from A, right? So you can get to them. So they're just separated by one resistor. So these 3 points, B, H, and F, should have the same voltage if you measure it, or like they should have the same effective resistance when you measure it. Similarly, we can go from another resistance forward, a resistor forward. So that would give us, for example, this one and also this one. So that would give us C, E, and G. So these 3 points should have the same effective resistance when you measure it. And lastly, we have D, which is the furthest from A, and it should have another resistor. It should have a higher resistance as well. Okay, so now we identify the symmetries. Let's try to break this up. Again, using the concept that when we have the same voltage, we could actually just condense them into a single point. So a bit like what we're doing here. So because these are the same voltages, we could just put them here. We could just yeah, they could just be represented by 1 point on the circuit diagram. So similarly, here we could condense B, H, and F into 1 point, and C, G, and E into another point. And the points of B, H, and F should be separated by 3 resistors combining in parallel from A. Okay, this sounds very weird, but what I mean is if we have A here, so coming from A, then we'll have 3 resistors combining in parallel. So that is just this one, and this one, until we have this point, which is B, H, and F. Okay, and then we have another 6 resistors in parallel. Okay. Until we reach, so that's this 6 resistors that we have here. 1, 2, 3, 4, 5, 6. That's the 6 resistors we have here until we reach C, E, and F. C, E, and G. This is C, E, and G. And then we have another 3 resistors. With these 3 ones. Until we reach D. So that is D. So that's basically this setup, but in a sort of like simplified geometrically way, in a circuit diagram. So if each of these resistor has a resistance of R, I'm going to change the color here, of a resistance R, then at this point of B, H, and F, they should have the combined resistance here should just be R over 3 if we calculate it. It just be 1 over bracket 1 over R plus 1 over R plus 1 over R. So that's R over 3. So the effective resistance you have at B, H, and F will just be 1/3 of R. And then this effectively will be R over 6. So at the point of C, E, and G, okay, so this will just be R over 3. But this will be R over 3 plus R over 6 because this is in total a series circuit, which give you R over 2 in total at C, E, and G. This going to D, this is another R over 3. So at D, the total resistance will just be R over 3 plus R over 6 plus another R over 3, which will be 5R over 6 in total. So that will be the effective resistance that you measure from between A and D. All right, I hope this is clear, but I know it turns out clear a bit tricky, so any questions?
You've got loads of compliments on your method, actually. People saying, yeah, that makes it a lot easier. So yeah, I think you were good.
Yeah. Great. Yeah, any questions? Anything I could clear up? I mean, yeah, as long as you find points of the same voltages and you just sort of condense them into a single point, I think that simplifies the question a little bit. But by a lot. So yeah.
Oh, we've just had one last entry, just someone asking how you got the 6.
The 6 where?
Not quite sure. Let's give them a sec to come back to us.
Yeah.
Oh, maybe it means the row of 6 resistors.
Okay, why there's 6 here?
Yeah, I think that's probably it.
Let me try to.
And someone said, how do you know when they're in parallel? Oh, all the questions are coming in now.
Yeah.
I think everyone took a minute, went, I loved that method. Wait, I'm not sure.
Yeah. Okay, so let's go through this again. So there are 3 here. Okay, so let's establish the fact that B, H, and F are the same, all at the same voltages, so they're here. And then C, let me change the color. C, E, and G are another voltages, so they're here. And then we have D, which is here. Okay, so then the next step is to find how many resistors that we have in between. So between A and BHF, we have 3 resistors in here. Okay, let me use blue. So 3 here. That's why we have 3 parallel. They are in parallel because it's like, all right, let me try to open my video. Okay, so let's try to imagine this way. So if this is A, and we just have 2 resistors, not 3 here, so they will be coming out this way. So in 3D they might be in different directions, but if you just collapse them into 2D, they're just coming out from the same point of voltages, which is A, and then going back to the same point of voltages, which is B, H, F here. So they are effectively in parallel, if that makes sense. And that's 3 resistors in parallel that we have here. So that's 3 here, 3 here. And then between BHF, so between these 3 and these 3, let's just count how many we have. So 1 here, 2, 3, 4, 5, 6. So that's why we have 6 here. And then between the green point, sorry, it's beginning to be very messy, and D, we have another 1, 2, 3. So that's another 3 here. if that makes sense. I hope that clarifies a little bit.
I think so, yeah. What I'm going to do is I'm going to dismiss the questions that were asked because I think you covered them. And then what we can do is just wait a second and see if any more crop up.
Okay.
See if we get any new ones coming through. So the new ones that have come through say, is there a reason why you don't account for current flowing through other points? For example, taking it B and accounting for current flowing from A to H to C to B.
A to H to C to B. So the way I'm thinking about it, because B and H are at the same voltage or current, no, at the same voltage. So the current flowing from A to H to C to B will just be symmetrical. Like, it's a bit like, so if we're just, this is A, and then this is B, A, B, H, D. And assuming we're going away from C, and you have some other currents here and they're connecting to the other points. So because this and this are at the same voltage, so essentially there shouldn't be any, so we could just, there shouldn't be any current flowing between them, so we could just collapse them to the same point, if that makes sense.
I think we're good. Why not 3 branches and 2 resistors on each branch?
3 branches and 2 resistors on each branch. Let me try to.
Yeah, I don't think that would give us enough resistors, would it?
Yeah, we have
We've
12
both tilted our
resistors.
heads trying to picture it.
Yeah,
Then we're like,
yeah.
would that be enough? I think a lot of this is just interpretation, isn't it? It's just how you've personally broken up that cube.
Yeah.
I was typing an answer to another question that came up while you were there, while you're thinking about that. So I just had somebody asking, is the sample paper similar difficulty to the main paper? And what I was saying is that that sample paper is the only one where no, that sample paper is just for you to practice being on a multiple choice format. So it's not representative of the maths and physics balance or of the difficulty. Difficulty is 2018 to 2023. We've done a lot of work behind the scenes to make sure that that absolutely holds true as well. Are we good? Is there anything else that we need to say about our cube of resistors, do we think? We've got one more about path. We've got, couldn't there also be a path that goes kind of around and about? I guess this is, or at least I don't want to jump in, but this is a case of electricity is going to follow the sort of easiest path.
Yeah. And I mean, you could consider that, but also I think if you are to consider currents flowing in every single possible directions, then there'll just be a lot of current that goes from other points to other points, but has some joints in between as well. Like, for example, that follows from A to H, etc., to B, could share some paths with, for example, going from C to G, for example. And it will just be a bit harder to calculate that way if you are to calculate it explicitly that way.
Perfect, thank you. Why, I'm going to make everyone give you a lovely reaction round of applause and say thank you and let you go. And then we've got 5
you.
minutes and I will quickly answer any remaining questions about the PAT. Thank you so much. It's lovely to see you again. I'll see you in October when you're back in Oxford as well.
Thank you. See you. All right, I'll just chat. Thank you so much.
No, thank you for
you.
for coming and joining us.
Thank you.
So as I was saying, one of the great things I get to do in my role as Physics Access Officer is I run our undergraduate ambassador program, and I work with early career researchers, really established research in their work in public engagement. And the two people who have joined us today are two people who I work with regularly. They are wonderful, and I'm very excited that Wei is coming back to do her further study at Oxford as well, because it means I will get to see more of her. Lots of questions about the PAT, so I'm just going to answer a few of them in the next 5 minutes. I'm going to address difficulty first. So if you have a question about difficulty, wait to hear what I have to say, and then let's see if we manage to answer it. So the difficulty of the PAT, the reason I said 2018 to 2023 is that is how long the syllabus has been unchanged for. If you want to look back at old past papers from whenever they start, like 2006 on the website, something like that, up to 2018, they are fantastic practice. Pretty similar difficulty, but the syllabus was a little bit different, so you might find some questions in there that we wouldn't ask now. So 2018 to 2023, that is our difficulty level, and that will be the same difficulty that you can expect in this year's PAT. It was the same difficulty in last year's PAT. The only reason I left out 2024 was because we have not released that PAT paper. And a few of you have asked, can you have access to that? The answer is no. Because it was an online format and it was developed from a very small question bank, but nonetheless a question bank, not everyone sat exactly the same PAT. There were 1 or 2 questions that were different. So we don't have a definitive version to share with you. But fortunately, you don't need one, because we've made sure that the syllabus is unchanged. All those questions are really similar. That also then, I think, answers questions. There's another one. Does everyone get the same questions in the PAT this year because it is multiple settings? The answer is no, not exactly the same. Everyone will get the same balance of maths and physics. Everyone will get the same balance of difficulty, but there will be a range of questions, and that's so that we can ensure fairness from the people who sit the PAT, the very first sitting of the first day in the first time zone up to the last sitting on the last day in the last time zone. So we have to work in time zones when we end up doing the PAT. What I will tell you is, behind the scenes, you might find it interesting what we do. So behind the scenes, we have specialist data analysis teams who ensure that our distribution of scores each year indicates that the level of difficulty has been consistent across the years. They are excellent. They're able to compare the exact questions that people get and make sure that we're able to accurately compare everyone's scores. What we then also do occasionally, if we've got a couple of spare particle physicists, is completely anonymize all of the data, so they've got no way of possibly knowing what questions relate to what. We set them loose and we just say, can you find any weird patterns in this data? Their day job is identifying weird patterns in the data that comes out of CERN. So when we release them on your data, they're able to look for patterns and go, no, this looks absolutely great. And they're like our backstop check after the professional data analysts have had a go, which is really good fun. They don't impact anything. It's just a little project for them to go and have a look and kind of keep us going. We're very much a department of physicists, ran by physicists. So those of you who are asking who sets the PAT, it's our physicists. It's the people who are going to teach you, hopefully, for the next couple of years. And all of those questions are gone through. Behind the scenes, what takes the most time is working out which wrong answers to put in the multiple choice. So those wrong answers, there's never one that's weird. We never guess a couple. What we do is we work out where are people likely to go wrong, and the wrong answers then represent those paths. So actually, we've got a really good idea of what you did from exactly what you select. We're able to say, they went wrong at that point. They went wrong at that point. they followed this path instead, and we get a huge amount of information from you. So I think that answers loads of the questions about difficulty and about the PAT in general. Someone's asked, are there solutions? And again, no. And this is because the PAT is not the same as school exams. Wherever you are in the world, school exams are marked in such a way that there is a certain answer. The PAT is marked so that we can understand your thinking process. And even with multiple choice, that is what we're interested in. So there is not a fixed set of solutions. And if anyone is telling you they have an official set of solutions, they don't. What they have is their solutions. So our students today have presented you with their best solutions to these workbooks. So it's a completely different way of thinking about it. Someone's asked, will I be at Open Day? I will be. So if anyone is coming to Oxford on Friday this week, in 2 days' time, I will be there. I will be hanging around for most of the day. I'm quite recognisable because I'm very loud. And I'm also presenting a couple of sessions for your adult supporters. So if anyone is coming with adult supporters, they're welcome to come and talk to me so that our tutors can do the most important thing, which is talking to you. Somebody has said, when applying on UCAS for physics, I could only find one course. It's the MPhys. Yes, our courses are what we call integrated master's courses. So you apply for the MPhys. It is a 4-year degree, and at the end, you come out with a Master of Physics. If during the course you change your mind, you can take the bachelor's instead, but we only take applications for the MPhys. So I think I've got most of those. Somebody's asked what college has the most undergraduate physicists. I'm not actually entirely sure, but I'm going to use that as a jump off point to say that our principles of admissions in physics is that you are not discriminated against based on where you apply from or where you apply to. So we do lots of work behind the scenes to make sure that we fully consider everyone's background, to make sure that everyone has an equal chance of admission. And we do a lot of balancing out the numbers so that whatever college you apply to, if you're good enough, you will get a place somewhere. That means that if a college interviews 10 people and all 10 of them are amazing, but they can't offer them all places, those 10 people will always get places somewhere. Likewise, if a college interviews 10 people and goes, I'd maybe take 2 of them, they only need to take those 2. But that's not going to happen. You're all going to be amazing. I think we have come to the end of tonight's session because it is 8 o'clock. If I haven't answered your questions, please feel free to drop me an email. So you all get emails from me all the time. Reply, do answer your questions. We are here to support you through your application journey. So if I haven't quite got to you tonight, that doesn't mean I don't want to answer you. We've just not quite had time. Drop me an email. I can see there's a few questions about predicted grades. Send that over by email. I will read it. I will get back to you usually within a day or 2, and I'll see you really soon. Okay? Thanks everyone. Have a lovely week. I'll see you next week for our final study focus session.